So our next speaker is going to be Ben Greenman, and he's going to be telling us about their work on how profilers can help navigate type migration.
Excellent. Thank you, Manu. All right, so this work was supported by the CRA. I was a postdoc. I've since graduated from the postdoc position, and now I'm an assistant professor at the University of Utah. This paper is all about how do we avoid runtime costs using off-the-shelf tools. In this case, the costs come from gradual types, and the tools that we're using are good old statistical profilers. So I'm really excited about this work because it tackles a question that I've had for a long time. So back in POPL 2016, we studied the performance of gradual type systems, and we learned two things. First, that big slowdowns are very common. 10x is on the low end of the slowdowns that we were seeing. And these were all over the place in terms of the possibilities that gradual typing allows you. Many of these possibilities are too slow to run in practice. But we also know that some good points exist, and these are spread throughout, we'll see an example of this, spread throughout the lattice of gradual programs that you can write. So we know these points are out there. How on earth do we find them? And we had some ideas, but we had no way of running the experiment and testing this until recently. And that's this idea of the rational programmer that made this all possible. So gradual types, where do these costs come from? First, here's some untyped code. I've got an untyped function that computes an average of the grades column of a big grading workbook. On the right, I've got a few calls to the average function. Since this is an untyped language, we can call the function with any arguments that we want. So the first call has a check mark because that's a good call. We're passing in an actual gradebook. And the second two are bad calls. And we can run these and see what happens in the untyped code. With gradual typing, we can change just the one average function. We can give that a type annotation and leave all the other code exactly the same as it was before. So this is a well-typed, gradually typed program. If we were to run this program, we would see two runtime errors when we do those two bad calls to average, but we don't see those until we run. So static time, we only check the types in the yellow part of the code. To do this and have sound types, we're going to need runtime checks, and that's where the costs come from. How much these checks cost? Well, it depends on the semantics of your gradual types. So there's at least two ways of doing the semantics. I can get type soundness, one with the guarded semantics, and this will give us what I'll call deep types. So one way of implementing gradual types is to say I'm going to use contracts at the boundaries between my yellow code and my untyped code, and those contracts are going to guarantee the types. Another way of working is the transient semantics. So this gives us what I call shallow types, and shallow types are implemented by rewriting every line of typed code. So whenever typed code does some operation, we have a quick check, quick assertion that makes sure that the shape of the data that we're getting matches the shape that we're expecting right now. So to put this in terms of our gradebook program, if we have the deep semantics for types, we're going to be checking the entire gradebook once that book crosses the boundary. So that's a big traversal of the data if it's a mutable data structure. And if the gradebook happens to be mutable, we're going to need to put that inside of a wrapper. And now every operation on the gradebook later on, that will pay some cost from that wrapper. In the shallow world, we're going to have a quick check that the thing crossing the boundary is a gradebook. And then when we pull numbers out of that book, we're going to have another assertion that makes sure those are actually numbers and not whatever we would have inside the recipe book. So with these two different semantics, we could wind up with very different costs. I've got 9x as the big slowdown from deep types, and it might be 1x after all for the shallow types. Great. Now, if we were to keep migrating this program and go to a fully typed version of it, we can no longer do those bad calls to average. Those will be ruled out statically. But when we run the program, we now get two different profiles. The deep types have no cost now because we have no more boundaries between typed and untyped code. The shallow types have a slightly higher cost than before because we've added more typed code to the program. So shallow is paying for every line of typed code. Okay, so now, let's see. We can use deep types, we can use shallow types, we can also use both of these in the same program. And this is work I did last year at PLDI. So we have a large space of possibilities. This is that gradually typed lattice. If we started out with 2 components in the program, we now have 9 possibilities. If we go a little bit up. And this raises a big question about once we're at a bad point, like that 9x, where do we go to improve it? There's lots of different ways that we could imagine migrating the program. If we have a slightly bigger program with 3 modules, now we've got 27 points. A tiny bit larger with 4 modules, and the picture barely fits on the slide anymore. So we have a huge search space, and we don't know ahead of time what point in this lattice a developer is going to wind up in. We've got someone who's using gradual types, they're going to pick, basically, to us, an at-random point in this lattice of possibilities, and it's our job as the system designers to make sure that the programmer can quickly navigate to a point that has better performance. Adding types by itself is a bit of a bike shed. You're not adding any functionality to your program. So now that you have to debug these types because they're adding slow runtime, that's even worse. So we want to make this as painless as possible, and that's what motivates the use of off-the-shelf tools. Can we use a profiler, treat the program as a black box, and then navigate to slightly better performance? We're working in typed racket. We have two profilers that we can use. First is the good old statistical profiler, and the second is a slight refinement of that called the contract profiler. When we run statistical profiler, we see output like this table. So we have one row basically for every function that can appear on a call stack. And statistical attributes cost to those different points, those functions. I've highlighted in blue and in orange the two important outputs that we get from statistical profile. So we care about what's the total % of time we spend at each point, and it might also be interesting to see what was the self-time in each point. So these two columns, blue and orange, are going to be important in a few slides. The contract profile starts with the same data as statistical profile, but it filters out everything that's unrelated to contracts. So now the report that the contract profiler generates is a list of boundaries ordered from what's the most expensive boundary to the least expensive boundary. So this will directly get us what's the cost of these deep gradual types. So contract profiler, there's just one output we care about. What % of the time do we spend doing this contract? Okay, and these two different profilers, we expect them to behave better or worse in the two different semantics for gradual types. So if our slowdown is due to deep types, the contract profiler should be very well suited to figuring out where are those deep costs. The statistical profiler with total and self, that's less suited. It may help and it may not. With shallow types, the contract profiler should be no help at all because shallow types are not using contracts. They just won't show up in the contract profiler. So then we need to turn to the total % and the self % from the regular statistical. And this is where our problems really start, and this is where we stopped back 6 years ago. We didn't know how to proceed because there are many ways that we can migrate the program, and now there's many different inputs that we can use as a programmer to decide what's the expensive part of the code that I need to focus my migration on. The answer now is to run a rational programmer experiment. So the idea here, bring in a human expert to identify what are possible strategies for doing the migration. Let's get as many strategies as make sense and then put them together in a head-to-head competition. Strategy number one, for this talk I'll call it the deep strategy. Once you've identified a slow boundary, and there's 3 colors here, yellow, blue, orange, because there are 3 ways that we could identify which boundary is slow. Once we've identified that on the left, convert both sides of the boundary to use deep types. The paper goes into a lot more detail about how this deep relates to what a programmer would be thinking. But for now, find the slowest boundary, migrate both sides to deep. We have a similar strategy for shallow. Find the slowest boundary and turn both sides into shallow. So that's another way that you can, another strategy, another algorithm that you could follow for making these modifications. Shallow also has 3 variants because it could be working with one of 3 types of profile input, but I've left off the colors here. And that's because for the next strategy, there was no space for the colors. The type-aware variant puts a priority order on which boundary to look at. So instead of finding the most expensive one, we want what's the most expensive one that does not require any changes to the types. And if there are no such boundaries, then we'll look at migrating untyped code. So number 1, that's if I have a deep, shallow boundary that's expensive, change the semantics so that they're either both deep or both shallow, depending on if we're on the left side or the right side strategy. And then second, if there's none of these deep, shallow boundaries, then take some untyped code and add types to that. And the reason this one makes sense is because adding types is work. So we skip the work if we can. One other strategy we have is looking at the whole program. What % of that whole program is typed? If less than half the program is typed, use shallow types. If more than half is typed, use deep types. And there's a good reason this makes sense, but I'll leave it for after the talk. And then finally, we have 2 other baseline strategies. The null hypothesis strategy says randomly migrate a boundary to randomly use deep or shallow types. And the PLDI-22 strategy is a one-step strategy. It takes your current program, turns all the typed modules to be deep or all the typed modules to be shallow, and then stops. So this in prior work was a way to get an order of magnitude improvement, and we'll see if it's successful or not in our experiment. Okay, so now finally, here's the setup for the rational programmer experiment. For all starting points and all the lattices, explore a path towards good performance. What is a fast configuration? That's one that runs at least as quickly as the untyped code. So you're doing at least as well as you were when you had no gradual types at all. And when I'm talking about paths, there's two criterion that we're going to use for them. A strictly successful path is like the first one on the bottom. Performance could start off very slow, 99x, stay very slow as long as it gets no worse, and then if we finally get to a 1x configuration, that was a strictly successful path. We'll also loosen that to allow a certain number of slowdowns along the way. So if I start at 3x, bump up to 99x by following the profiler, but then eventually get to 1x, that's successful in the one loose sense. We collected a very large data set to run the experiment. We started off with 16 benchmark programs that gave us 100,000 gradually typed configurations. It took 1.2 million measurements to collect all the running times and profiling times that we needed, and that produced 5 gigabytes of output. So we could not have done this work without the help of Cloud Lab, which gave us plenty of single user machines that we could collect reliable numbers on. So thank you, Cloud Lab. And now let's see the results. We're going to use these skyscraper plots so that we can see a strict success and looser successes on the same figure. So our bars will get thinner as we go up, and that'll be looser and looser. But first we'll focus on strict success. The x-axis here is our different strategies. The y is the percent of all scenarios that they succeed on. Here's some example data. This is the kind of thing that we'll see in the full results. Here, every strategy is a failure except for shallow, which always succeeds no matter what profiler you use, and random succeeds half the time. That's the example data. Okay, now real data for strict success. So we see yellow is much higher than anything else. The contract profiler is the most successful out of all of these. The statistical profiler is not helping us reach these 1x configurations. We also see that when we look to statistical, using the total column or using the self column gives us equivalent results. Neither one is much better than the other. The other thing that really stands out is the deep strategies are far better than the shallow strategies. So shallow and type-aware shallow are near 0. And all three deep strategies are close to one another. So choosing to be type-aware and delaying the work does not much affect the overall success. And also choosing to be lattice-aware, that's along similar lines. Randomly changing boundaries is not very successful, and toggling is also rarely successful. So now what if we loosen things? Let's look at one slowdown along the way. Well, things get a tiny bit better, almost 10%. About 2, 3 loose. Again, incremental improvements. N loose says I'll tolerate any number of slowdowns along the path as long as I finally reach a point that's a fast configuration. N loose is a huge win for random. So randomly changing boundaries, you can get lots of degradations, and sometimes it winds up in good places. But the surprising thing is it does not help the others very much, and especially it does not much help our already successful strategies. So the best ones that we have here are not much better by adding looseness. This was a big surprise to us. One more plot to look at. What if we change the goal line? So instead of looking for something that's a 1x slowdown, just as fast as untyped, we look for 3x. And we see that this helps the shallow strategies a bit. So they're able to achieve a 3x goal line, but it does not help the others very much. So if we were already successful at the 1x mark, changing to 3x doesn't make things much more usable. All right, to wrap up, we have two sorts of takeaways, low-level takeaways and high-level. So at the low level, if you're a programmer using gradual typing, the best way to go for using the profiler to navigate type migration is to go with contract profiling and optimistically go towards deep types when you make a change. Second, we found shallow types do not help much as a stepping stone towards 1x performance. I was very surprised by the shallow types thing. I thought for sure, shallow, you can use that to avoid an order of magnitude slowdown and then take a few more steps to get to a fast point. It seems like that's not a recommendation that I can make at this time. And this points towards some ideas for future work. One, can we find a better hybrid strategy that mixes deep and shallow? And then two, what about a shallow-specific profiler? Contract profiling is tailored toward deep types. Statistical profiling is not tailored toward shallow, so maybe we need a better profiler. At the high level, this rational programmer idea is a powerful tool for enabling rigorous experiments. We could not have done this work without the thinking guidelines that rational programmer gave us. And it's been useful in the past for studying error messages as well, and I think this technique has a very bright future in testing other pragmatic questions about programming languages. The end.
Okay, questions? Anyone? And again, please come up to the mic if you have a question.
Hi, thanks for the talk. I was wondering if you had any statistics for loose, like 1 or 2 loose for strict, for 3x. Because in your...
Yep. So we also have looseness for the 3x goal line. So what that would look like on a skyscraper is more thin lines on top of the already thin line.
Okay.
It's not very exciting.
I see. Thanks.
Hello. So would you use this output to kind of say that if you're starting from an untyped language, that adding like the deep typing is better for performance than the shallow typing?
Adding the deep typing is better if your goal is to reach something that's as fast as the untyped code was.
Yep. Okay.
So, but we also know from prior work that deep types can add these huge multiple orders of magnitude overhead. Shallow types don't do that. They tend to stay under 10x. So I really think that you want both. But if you're going towards fast and fast is what you want, go for deep.
Awesome. Thank you.
Okay, while you're setting up, let me ask one last question. I didn't quite follow why your statistical profiler wouldn't expose the time spent in contract checking. Like, why do you need a separate contract profiler? Why isn't the statistical profiler, why can't you just take the data and say, this is how much time we spent in contract checking?
Right. So statistical profiler is getting all the different things that can add to your stack. It's tracing all functions and all contracts. So the contract data is mixed in, and it can be diluted by the amount of time you spent doing actual work inside of a function. So statistical will point you towards this was the slow part of the program, but I don't know if that was slow because of gradual types or slow because I was doing some important computation.
Okay. We can talk more offline. Okay, thank you very much. Let's thank the speaker again.